We're going to do an extension on circulation and flow, which is the work integral, and then we're going to do flux in two dimensions. So we'll start out with the work done of F over the curve in the direction of increasing t, where F is given by this field, and the curve R of t is given by this. So we know that in order to find the work done, our work is going to be equal to the integral of c of f dot dr, which simplifies to the integral over c of f of dot dr dt, dt, which eventually becomes the integral from, well, t equals a to t equals b of the field evaluated at the curve, so evaluated at r of t, times the derivative of r of t with respect to t. So in order to find this, what I have to do is I'm first going to have to figure out what the curve is evaluated at r of t. Knowing that if I put this in parametric form, this is the x coordinate, this is the y coordinate, this is the z coordinate. So wherever you see x, y, and z, you're going to put the appropriate coordinates in there. So f evaluated at r of t is going to be f of, it's x comma y comma z. But we know that x is going to be equal to t squared, y is going to be equal to t, and then z is also going to be t, so t comma t. So plugging in the appropriate values, we know that we're going to have f, x is t, y is t squared, so this is t squared times t I plus y, which is t, so this is tj, minus yz, so y being t, z being t, so minus t times t in the k direction. So we have t cubed I plus tj minus t squared k. Now we're also going to have to find dr dt. So this is r dr dt is going to be 2ti plus 1j plus 1k. So we found this and we found this. Now we have to take the dot product of these two. So taking their dot product, f, I'm just going to say dot dr dt, is going to be multiplying their corresponding components. So t cubed times 2t is going to be 2t to the fourth plus 1 times t plus 1 times minus t squared. So this is going to be a minus t squared. And now we have this dot product, which means we can integrate this from t is equal to a to t equal to b, so from 0 to 1. So our work is going to be the integral from 0 to 1 of this polynomial represented in t, so t to the fourth plus t minus t squared dt. And this polynomial being relatively simple to integrate, we know this is going to be 2t to the fifth over 5 minus t squared over 2, plus t squared over 2 minus t cubed over 3, evaluated from 0 to 1. So this will be 2/5 plus 1/2 minus 1/3, plug in 0, everything's going to be 0. So we have 17 over 30. All right, so I'm going to erase this and I want to show you a different way of doing this using the differential equation. So the differential equation for work is the integral over c of m dx plus n dy plus p dz. And this is nothing more than the expanded form of really that dot product. We know that this function f can be written as, or this field f is mi plus nj plus pk. So this function being your m, your y being your n, and minus yz being your p. So when I want to find this, I just need to know what m, n, and p are evaluated at r of t. So what I know is I know that m is equal to xy, but I have to evaluate at r of t to know that x is t squared, y is t, so this is going to be t squared times t, so this is t cubed. N is going to be our y, but it has to be evaluated at the curve, so this is going to be t. And then p is going to be minus yz, evaluated at the curve, is going to be minus t times t, or minus t squared. If this looks familiar, like we've already done this before, it's because this is just a re-representation of exactly the same thing. Now we still have to find dx, dy, dz. Now notice that if I write this in parametric form that x is equal to t squared, y is equal to t, and then z is equal to t. This is just parametric form of that curve, and that's how I was able to evaluate these things in x, y, and z. So if I want to find dx, well, this is going to be 2t dt, dy is just 1 dt, and then dz is just going to be 1 dt as well. So when I set up this integral, we know that this is going to be the integral over the curve, but now once I've evaluated that at your x, y, and z, you can use your t value. So from 0 to 1 of m, which is t cubed, dx, which is 2t dt, plus n, which is t, times dy, which is 1 dt, plus p, which is minus t squared, and then dz is going to be dt as well. And then when we simplify this integral from 0 to 1 of 2t to the 4th plus t minus t squared dt, and we can see that we get exactly the same thing. This is 2t to the 5th over 5 plus t squared over 2 minus t cubed over 3, evaluated from 0 to 1, which is that 17 over 30. Now the reason why I put this in this form is eventually we want to be able to do the line integral and also the flux integral, and if you can write this in the differential form of mdx plus mdy, we can do flux very, very similarly. So let me set up the next problem. So I want to evaluate the line integral of the plane. Now what we've written is the line integral in this differential form. So I want to do the integral of this along the curve y is equal to x cubed from the point 1, 1 to 2, 8. Now if you look at this form, this looks a lot like the integral over c of m dx plus n dy, and that's because it is. This is nothing more than the work integral or your flow integral. Now, in order to do that, we're going to have to figure out what x and y are in parametric form. So if you want to write it in r of t or just parametrics, and then I have to be able to define, m and n, which are these two functions, at those particular values. So the way we put this in parametric form is you let x equal t, and if x is equal to t, then y would be equal to t cubed. So y is going to be equal to t cubed. And if you want to write this in r of t form, you can say this is the same thing as r of t is equal to ti plus t cubed j. And then you have to figure out what t values are going to make it go through 1, 1, and 2, 8. So if you plug in t equals 1, this will be 1, and this will also be 1. So this is from 1 less than or equal to t less than or equal to, and how I get 2 comma 8 is if this is 2 and this is 2, this will also be 8, so this will be 2 comma 8. So this is when t is equal to 2, you get the point 2 comma 8. So now I know x and y, so I'm going to have to find, what is m? Well, m is equal to xy, evaluated at x is equal to t and y is equal to t cubed, so t times t cubed, so this is t to the 4th. N is equal to x minus y, x being t, y being t cubed. And then we also have to do your dx and your dy, so dx is going to be just 1 dt, and dy is going to be equal to 3t squared dt. So now when we set up this integral, this is going to be equal to the integral from, 1 to 2, m, which is t to the 4th, I'm missing work here, t to the 4th dt, plus n, which is t minus t cubed, times dy, which is 3t squared dt. And simplifying this, the integral from 1 to 2 of t to the 4th plus 3t cubed minus 3t to the 5th dt. And again, this is just a polynomial, so it's easy to take its antiderivative. So t to the 5th over 5 minus 3t to the 4th over 4 minus 3t to the 6th over 6, so t to the 6th over 2, evaluated from 1 to 2. And plugging in those values, you have 2 to the 5th over 5 minus 3 to the 5th over 4. That's not right. This is 2 over 4 minus 2 to the 6th over 2. Subtracting when you plug in 1 to the 5th over 5 minus 3 times 1 to the 4th over 4 minus 1 to the 6 over 2. So what I got was 2,444.35. All right, so this is going to move us into flux because we need this kind of notation, your m and n and your dx and dy. So I erase it, I'll come back. All right, so we're going to do flux in a plane. So if I have a plane here, then these are the field lines F, and red being the curve. If I kind of zoom in with, this is your field line of F, and this is going to be your curve. We know that the work is the integral of f dot t, because what we want is we want to know what this does in the direction of the curve. But when we're asking about flux, what I want to know is what it does like against the curve. So what we can do is we can think of flux maybe as like say a three-dimensional pressure vessel here. Circulation would be around this, but if I want to know about flux, like say if I have this thing under pressure, flux is what pushes against the wall of this coffee cup. So we can see that if this is pressurized, all your flux is going to be perpendicular to the wall of this cup. So that's what we want, is when we want flux, we want to know perpendicular to the direction of this curve. This being the three-dimensional function, this just being a two-dimensional curve. So this is the 2D version of that. We'll get to 3D soon enough. So flux is going to be the integral over the curve of f against the curve. So f dot, it's normal, ds. So we know that ds isn't useful. I need to turn this into dt. So we know that n is going to be the unit tangent vector across your t, because it needs to go here. You're going to cross it with your k, I mean. So t is dx dsi, dy dsj, and then 0k because we're talking about the plane. And then k is 0, 0, 1 when it comes to ij and k. So doing your cross product through your matrix, we can see that we get dy dsi minus dx dsj. And now I'm going to do f dot n, so mi plus nj, dotted with this, dy dxi minus dx dsj. So we're going to get m dy ds minus n dx ds. So plugging that in here, we're going to have the integral over c of m. We're going to have dy ds minus n dx ds with respect to s. So this ends up looking very similar to that work integral. And if you guys remember doing your work in calculus 3, we would have to find the unit tangent vector, then eventually the unit normal vector. In some of the problems, you could see that the unit normal, you just took the coordinates, you switched them and made them negative, and that's kind of why it looks like this. So this is just kind of a quick check of showing that this is the work along its perpendicular as opposed to along its parallel, along its tangent. So if you know m defined at x and y, and n defined at x and y, and then you know your dx and dy, this integral handles much like your work integral. We just have a different order here. So let's set up a work and flux integral, and you can see that how similar they really are. So if I want to find the circulation and flux of this field over this curve, again we're going to have to find the parametric of this, your x's and y's, so I can evaluate that your m and n function. So we know that this is a circle, so we use r cosine t, and y is going to be equal to r sine t to take a circle and turn it into parametrics, where r is going to be the radius of the circle, so r is just going to be 1, so this is going to be cosine t and sine t. Of course, you can write this as r of t is equal to cosine of ti plus sine of tj, where 0 is less than or equal to t, which is less than or equal to 2 pi, and that's because I need the entire circle. So we go back through our m and n and your dx and dy. So m is going to be equal to x. Now x is going to be the cosine function, so this is the cosine of t. N is going to be equal to y, and y is this, which is the sine of t. Now you're going to also need your dx and dy, so dx, derivative of cosine is minus sine of t dt. And then your dy is going to be the derivative of sine, which is cosine of t dt. And then we can set up your circulation. Now your circulation is the same thing as work, except circulation is through this closed loop. So the circulation is going to be the integral of the curve. And if you see some closed loop, that just means that the curve runs into itself. Of So this is going to be equal to m, which is integral from 0 to pi. M is going to be cosine of t. Dx is going to be minus sine of t dt. I'm just going to leave the dt all on the other side, so minus sine of t. And then plus n, which is going to be sine of t, times dy, which is cosine of t dt. So I just pull the dt all the way out. And we can see that these will add to 0. So this is going to be the integral from 0 to 2 pi of 0 dt, which is 0. So this has 0 circulation. Now, if you want to do flux, it's very similar. So your flux is going to be the integral over this closed loop of m dy minus n dx. And we already know m and n and dx and dy, so it handles very, very similarly. So this is going to be the integral from 0 to 2 pi of m, which is cosine of t. Dy is also going to be cosine of t dt. I'm going to pull the dt over here again. Minus n, which is sine of t, times dx, which is going to be minus sine of t dt. So there's your dt's. So we get the integral from 0 to 2 pi of cosine squared of t plus sine squared of t dt. So this is going to be the integral from 0 to 2 pi of 1 dt, which is going to be t evaluated from 0 to 2 pi. So this is equal to 2 pi. And I want to show you the field, and so I can explain why this has 0 circulation, but it does have flux. So if you remember this field, which was introduced in a previous video, this field looks like a kind of an explosion field that you have at 1, 1. It's going to be here, so 0, 1, 1, 1, and then so on. So that field is going to look like this. And as you go further out, they actually get larger. And if you look at this circle of radius 1 through here, you can see a circle. I'm just going to make it a little bit bigger so you can see hit the lines. But that circle of radius 1, if you look at this explosion, it's not really going to move a particle on this circle around this curve because all these lines are perpendicular to the curve. So if I drop the particle there, all it's going to want to do is just push against the edge of the circle. So it's going to have 0 circulation. But since all of these field lines are perpendicular to the curve, every one of them basically presses on this curve. It gives it that outward force, and the outward flux or the outward force of these field lines on this curve is 2 pi. So if you really want to know if your pressure vessel can hold that, you really have to check the flux of that pressure vessel to make sure that the flux isn't larger than its material strength. And that's it.